Okay. So, like I mentioned, we're doing the same thing for quantitative data that we did for categorical data. Yesterday, we learned about tables and graphs. Tables and graphs. We're going to do the same thing for quantitative data, table and graphs, but we're going to do it backwards. I'm going to start with the graphs, and then go back to the tables on Friday. Because for quantitative data, the graphs are actually easier. The tables get a little messy. Weird, right? Yeah. We'll learn why on Friday. So we're going to start with the graphs. In order to draw graphs, I have to know which type of quantitative data I have, because numbers fall in two groups. I can have discrete quantitative data, and I can have continuous quantitative data. Discrete and continuous. Continuous, we've definitely heard in previous math classes. Yeah, we know the number line is continuous. It's made up of an infinite number of points. You can have 1, you can have 2, 1.5, 1.25, 1 2/4, 1 all the way down in there, right? That is continuous, infinite number of values. I can divide it into fractions and decimals and pieces and chunks. Yeah. In statistics, these values are typically things that are measured. I need a device to measure them. For example, height is a continuous variable. I need a measuring tape or a ruler to figure out exactly how tall I am. And if you measure me in the morning, I'm just a little bit over 5'7". It's not exactly 5'7". You measure me at the end of the day, I'm just a little bit under 5'7" because my spine goes squish over the course of the day. But I need to measure it, and I am going to get fractions and decimals. That's here. I want you to take a second and turn to your group mates and see if you can think of another example of something other than height that is continuous. In about 90 seconds, talk to your neighbors. Things you would measure. All right, we're going to go around the classroom, pick on some people. Ricardo, I'm going to start with you. What did your group come up with? Mass? Yeah, mass will work. It could be mass of air, or mass of humans, or mass of some unknown gas, yeah? We need a scale to measure mass. Yeah, good. Chris, what did your table come up with? Space? So area or volume? Yeah, okay. Yeah, those are things we measure. Very good. Very good, very good. Anna Jade, what did you guys come up with? Speed, yeah. Speedometers on our car. The little needle can sit between two hash marks. Yeah, very good. Anything you need a device to help you measure. Time is another one. Even though we typically think that we're counting seconds on our fingers, no, there are fractions of a second and fractions of a fraction of a second. That's a measured quantity. Time is also continuous. Yeah, very good. Now on to the slightly weirder word, discrete. Have we heard that word before? Have we heard it in a math or science class before? No. I got a lot of discretes about being sneaky about how you do something or covert. Yeah, which is true if you're in a language class. In a math class, discrete has to do with what that number does, how it behaves. In math and physics, discrete things are things that cannot be subdivided into smaller pieces. Yeah. So at some point you probably learn, if you're in baby physics, that electrons and protons and neutrons are discrete. We can have 1 proton or 2 protons. We shouldn't have 1.5 protons. And then you get to more advanced physics and you learn there's quarks. A better example would be oranges. If you go to the grocery store, you can buy 1 orange. You can buy 2 oranges. If you take out your pocket knife and try and cut an orange in half, the grocery store is going to be very angry. Oranges are sold in discrete quantities. These things are countable. I can count them on my finger. No oranges, 1 orange, 2 oranges, 3 oranges. Yeah? Yeah. Students, 1 student, 2 students. I should not have 2.5 students. Whole numbers. Another example before I asked you to come up with some. It came up this morning. Shoe size. Shoe size is discrete. It goes from 9 to 9.5 to 10. You do not find shoes that are sold 9 1/4, 9 3/4. They are discrete numbers. They aren't whole numbers, but they are numbers that don't subdivide further. I go 9, 9.5, 10. There isn't anything in between 9 and 9.5. Shoe sizes would behave as discrete in statistics. There's like a finite stopping point where I can't divide them any further. Good. Take a minute in your groups, turn to your neighbors. Give me another example of something that's discrete in statistics. All right. Let's start going around the room. Nancy, what'd your table come up with? The age? If we're counting the number of years that you've existed on planet Earth, yeah, we would count 1 year, 2 years, 3 years. That could be countable. Yeah, absolutely. Very good. Valeria, what did your table come up with? Cars? Number of cars in a parking lot would work, yeah? Number of cars in a parking lot, number of cars that have passed by a laser that's counting cars on a road, yeah? Very good. Very good, very good. We'll do one more, Amanda. What did your table come up with? Number of desks, yeah. Number of desks in each classroom. It's going to vary depending on how big they are. Yeah. Notice 2 of those 3 things are phrased as number of. Number of. Technically, age is number of years. Things that are discrete, more often than not, can be written as number of fill in the blank because they are countable. Very good. How we graph them depends on where they fall. Today we're going to focus on the countable guys. When I see you on Friday, we're going to start talking about how do we graph the continuous guys, because we know they behave differently. Yeah? Good. Okay. Let's go ahead and talk about our 2 graphs for today. Yeah. We're going to start with dot plots. Dot plots. Dot plots are my favorite type of graph for discrete data because I feel they're easiest to connect. Did you make an e-hall pass? No e-hall pass, no go. No e-hall pass, no go. So first step, we're going to draw a number line. Horizontal line, hash marks that are evenly spaced. We know how to do that. Yeah. Draw a number line. And then we're going to make a dot above the line for each data value. Lines and dots, we can do that. I don't even need any art skills for that. So we have an example. It says construct a dot plot for the data shown below, gave us a list of numbers. If I'm going to make a number line, what do I need to know about my numbers? The range, very good. I need to know how wide it is. Where does it start? Where does it end? Perfect. So we're going to look at the data. I see the smallest number is 1. That's my min. I see my biggest number is 14. Yeah, that's my max. So I should start counting at 1, should stop counting at 14. I can make it a little bit longer if I want, but I need to have at least 1 and at least 14. Oh. 7, 8, 9, 11, 12, 13, 14. We face. Check mark, halfway done. You'll notice hash marks are evenly spaced. If you were doing this on your homework, you would use a ruler or some graph paper to help you with that. You'll also notice I only labeled the even numbered hash marks because I'm lazy. We can assume that someone reading that graph knows that the number 3 sits behind 2 and 4. That is a safe assumption. And now I'm going to plot those points. I do this in order to keep myself organized so I don't miss something. I start at the left end of that number list. I cross them off as I plot them. So I'm going to start with 9. 9's between 8 and 10. I make a dot above the line. Not on the line, above the line. Repeat. For the next point is 11. I go to 11. I make a dot at that same height above the line. And then I run into an issue. My next point is the same as my last point. What do I do? Yeah, stack them. One on top of the other. Yeah, stack them. Yep. I need to indicate to other people there's a second 11, so I don't want to put them right on top of each other. Stack them. Make a little pile. Yeah, just like they were blocks. Yeah, good. I'm going to work my way down the list. Next one is 13. And then 14. And then 5. And then another 5. And then a 12. And a 2. I got 8. 1. Another 11. Another 2. Another 9. And another 12. You'll notice even while talking and drawing at the same time, that didn't take very long. I'm pretty fast. That's why I like these types of graphs. Of the ones we draw, they tend to go the fastest, and I'm lazy. If you are asked to graph or describe a discrete set of data, this is the graph of choice because it's the fastest to draw. Yeah. We could tell a lot about the data just by looking at that graph. As a practice statistician, I see that this data is top heavy. more of the data points are here between 8 and 14 than between 2 and 8. They have the same width of 6 here, width of 6 here, but there's more data here than down here. This data set is top heavy. We're going to give a word to that in a little bit. That matters because whether my data is nice and evenly spread or if it's slid to one side or the other tells me how I treat it when I start calculating things. Okay, questions on the dot plot? No. All right, we're going to do our stem plot next. All right. All right, stem plots, a little bit weirder. Very first thing we're going to do is we're going to take our numbers and we're going to split them into two pieces. Two pieces. The very last digit is going to be called the leaf. Picking off the very last number, separating it from the rest. That's called its leaf. The numbers that are left over, the remaining digits, are called the stem, which is why it is called a stem plot. We are going to organize the data by stem. Each stem is going to get its own row. And I'm going to do an example for you so you can see what this splitting process looks like. So I'm going to take that last number over here, that 33. Yeah. I want to pick off the last digit, so I'm going to put a divider between the first and last digit. This guy is my leaf. This guy is my stem. 33 has a stem of 3. It's going to be in the same row with all of the other numbers who also have a stem of 3. 34, 36, 32, 31. All of them have a leading digit of 3. They all go in the 3 stem. Challenge question. I want you to take a minute in your small groups and looking at that list of example numbers, how many different stems are in that set of data? We've got 90 seconds. How many different stems? How many rows am I going to need for my table? Try and come up with a cohesive answer for your table because we're going to vote by table in a minute. So what are we thinking? Probably 4 by 4. What are your stems? 1, 2, 3, 4. Where do those two numbers fall? 4 and 1. So if I cut that process, where does that dividing line go when there's a single digit? The stem and the leaf be the same? No. So is there like a leading zero? Like the zero come after? So that's a question. Does it matter where I put the 0 on the 1? Yeah, because if I put it behind the 1, it becomes a 10. That's a new number, yeah? So yeah. Yeah. All right, we're going to vote with our fingers. I need one person at every table, now that you've discussed, to tell me how many different stems there are. Show me on your fingers. 4, 5, 6, 2. I see a 5, I see a 5, I see a 5, I see a 4, I see a 5, I see a 5, I see a 5, I see a 4. And those are the same answers I got in all my other class periods. 4s and 5s. 4s and 5s. And the question is, what's the difference? Very good. We have two numbers that don't really fit with the rest of the set. I have a 1 and I have a 4 that are single digits. So the question is, what do I do when all I have is a 1? Yeah, and the next to it needs to be in front. Because if I put it behind, it goes from a 1 to a 10. That's a new number. So for single digit numbers, these are the only exceptions. Single digit numbers, you need to put a leading 0 in front, so they have 2 digits just like everybody else. So 1 and 4 have a stem of 0. 0, 1, 2, 3, 4. 5 stems. Yeah. So I need 5 rows in my table. So stem, leaves. Don't judge my English. I'm going to make my leaf rows long. 0, 1, 2, 3, 4. Come on. Come on. There we go. From here, it's kind of like a dot plot. I'm going to put the numbers in order in the stem that they belong to. The trick is they need to be in order from smallest to largest. So I cannot just work from left to right across that line like I did before. I need to work across that line from smallest to largest. We have to sort it as we go. So smallest number in my list is a 1. That has a stem of 0. That goes here. I should do that in black, but I'm not going to because I already started in red. Next smallest number is a 4. Also has a stem of 0. That goes here. Notice there is a gap between the 1 and 4. We don't want them sitting next to each other. It shouldn't look like 14. If I were typing on a calculator, I would do 1 spacebar 4. You won't see statisticians do it, but if that makes you feel better, you could. I won't dock you. I can't promise what the AP board will do with that. Though it's also unlikely they'll ask you to make a Stemplot. So it's more likely they'll ask you to read it. Okay, next digit. We're on to 2-digit numbers. I'm in the 1 stem. So all the numbers that have a leading 1. What's my smallest? 12. I've got a 12. I've got another 12. I've got another 12. I think that's it for the 12s. Are there any other ones? 18. Perfect. And 19. Yeah, perfect. I think that's it for the stems of 1. And now I need my 2 stems, the ones in the 20s. What's my smallest? 21. Perfect. A 1. 23. Okay. 23. And then 25. 25. 135. Perfect. Okay. On to my 30s. My 3 stem. Smallest 30s. 30. 2 of them, right? 30, 30. 0, 0. Perfect. 30. Is there just the one? No, there's two. Two 33s. 1, 2, 3, 3. Good. 30, 35. I think that's it. No, 38. 38. Yeah. 8. That's it. Yes. And staring at the board too long. We start with our 40s. Smallest 40 is 43. There's two of them. 43, 43, 3, 3, 44, 30. Where did it go? 46. There we go. That's it. A little bit longer than a dot plot. Not horribly so, but a little bit longer. It does show us the same type of information. I get shape from this graph. It's just now the shape is on its side. But I can still see that this data has two peaks, one in the 10s, one in the 30s. Out of curiosity, what's the prefix for 2? You're riding on a cycle that has two wheels. It is a bicycle. Bi means 2. This is a bimodal distribution. Bi means 2. Modal refers to the number of peaks. Bimodal has 2 peaks. 2 peaks. Stemplots with, what do you mean? So I'm glad you brought that up. Typically, Stemplots are used when you don't end up with more than about 10 rows, and you don't end up with more than about 10 digits per row. If you have values from like 100 to 150, that's reasonable, because then you have the 1, 0 as your stem, the 1, 1 as your stem, because you're only picking off the last digit. But if you have 100 to 9900, that's too many stems. So this is typically only used for stuff that's kind of close together on the number line. Yeah. That was a very good question. Other questions? Yes. Ooh, so as long as like that shoe size example where they were discrete decimals, 9, 9.5, 10, then yes, you could have 9.0, 9.5, and then 10.0, 10.5, that kind of thing, yeah. So you could do it with decimals that terminated, yeah. Matter of fact, I think your book does an example of that somewhere. It's less common, but it can be done. Other questions? No, you guys are asking good questions today. Okay, next thing is we're going to learn some new vocabulary to describe the shapes of the graphs that we're drawing, because that's one of the goals. One of the things you will be asked to do. I drew the pictures for you because I was feeling nice. We're going to learn some vocab. We're going to start with a review of some things you know. Yes? It could be. Yeah, I think you're looking at population growth and changes in population, which is very different than what we're looking at in terms of population data. No, that was good that you're making connections, but they look at growth, whereas we're looking at like height from a population of data at one time. Yeah, so different use of the same word. All right, the graphs on the top row all have one peak. Prefix for one. If I have a cycle with one wheel, it is a unicycle. Yeah, this is unimodal. All of these data are unimodal. Unimodal. You'll notice I'm writing it in the middle because there is another term that we're going to add to this. These are not just unimodal. Unimodal tells me how many peaks. I want another descriptor for where that peak sits on the graph. So for that first picture, where does the peak sit? In the middle. If I cut that graph in half, both halves look approximately the same. In math, we call that symmetric. This graph is symmetric about its center. We like symmetric graphs. All of semester 2 is based on data that it behaves as if it were symmetric and unimodal. Very good. That is not true of the other two graphs in the top row. The peaks are off center. We use the word skewed, which is fun to say. You will notice I have not written it down because we have to determine the direction of the skew. Yeah, this is what gives students nightmares. It upset me the first time I saw it because we're not going to understand why it's called this until next week. The skew tracks the position of the long tail, not the peak. In that middle graph, which side of the graph contains the long tail? The left, which means this guy is left skewed. If my pen would work, come on. Has to do with where the mean of the data sits relative to the median. We're going to talk about that next week. In a left skewed graph, the mean is to the left of the median. The other graph, the long tail is on the right, so it is right skewed. When we are talking about unimodal graphs, it is important to identify both that it is unimodal and whether it is symmetric or skewed. If it is skewed, which direction is it skewed? And we are going to practice. I'm not going to test you on it tomorrow. You'll be fine. I promise. All right, bottom row. This guy's a little weird. If I look at him, he's oscillating about like a single value. Some are above, some are below. But on average, this guy is kind of box-like. We would call that data uniform. Uniform. All of the categories are uniform. We won't do statistical analysis with uniform data. It is boring. The equations for it are on Google. They are pretty simple. The middle of the data is in the middle of the graph. Surprise, right? We're going to focus primarily on the first row for stats. We should be able to name the bottom three, though, by sight. We see them. We should know what they're called. That second graph, how many peaks? 2, it's bimodal. Very good. This one's bimodal. We saw an example on the first page. That last graph, how many peaks? 3, tri. Very good. We can call this trimodal because there are 3 peaks. Or close. Close, so close. Multimodal. I would not mark you wrong if you wrote poly instead of multi, but you're going to see the AP stats board write multi. Thank you. Perfect. We're running out of ink. So trimodal is more accurate, but a lot of statisticians, once you get past bimodal, it's multimodal. because once you get past bimodal, those data sets get harder to deal with. Good. So now we know how to label shape. If you encounter a problem that asks you to describe a set of data or to compare two sets of data, they don't just want shape. They want 4 things. And I remember them with the acronym SOCS. When you are comparing or describing distributions, use SOCS, S-O-C-S. Don't forget your SOCS. Shape, outliers, center, and spread. 4 things you need to describe 4 sentences in your paragraph. Yeah? Shape, outliers, center, spread. We know how to do shape. We just talked about it. You make a graph, you describe the shape of the graph. Yeah? How many peaks? Is it symmetric or skewed? Yeah? The next 3, we're going to fine tune over the next couple weeks, but I want us to have an idea of how they work. The next one is outliers. Have we heard that word before? Some of us, yes. Some of you are blank staring at me like I'm speaking Greek. So, to clarify, outliers are data points that don't follow the pattern of the rest of the data. Most of your data is between 5 and 10, but you got this one random data point out at 25, that's an outlier. It will stand out from the rest of the data in your picture. So this is another one, you look at your graph. You are right. We should stop for today.